Howdy! Welcome to Elementary Statistics. I'm Lance Curtis. This is the lecture for Section 8.4, Testing a Claim about a Standard Deviation or Variance. Here in this lecture, we're going to talk about testing a claim about a standard deviation or variance. So we'll start with the initial requirements that need to be met in order for our methodology to apply. We'll get into some of the details of conducting and concluding the hypothesis test. Look at some tips for using StatCrunch for conducting hypothesis testing on standard deviations, as well as how to calculate critical values in StatCrunch. And we'll conclude with a brief look at using confidence intervals on the population standard deviation. So, as just mentioned, here in this section we're going to introduce methods for testing a claim made about a population standard deviation or a population variance. Of course, this is going to be based on the chi-square distribution that we saw back in section 7.4 when we were creating confidence intervals on a population standard deviation or population variance. The same requirements we saw there are going to apply here. There is, however, one notable exception. The requirement that we have normally distributed data is going to be much more strictly insisted upon because the chi-square distribution is a skewed distribution. We're also going to have a different test statistic, which you see here on the screen. So we take our degrees of freedom, multiply by our sample variance, divide by our population variance, and that gives us our chi-squared score, which is our test statistic. As always, degrees of freedom is one less than the sample size. Let's talk about those two requirements that I mentioned earlier. We have two main requirements that we need to satisfy. The first is that the sample is a simple random sample. That's pretty much a given because this is pretty much a requirement for most, if not all, of what we've been doing so far. The second is that the population has a normal distribution. And as I mentioned, we're going to be more strictly adherent to this requirement than we were before. That means we can't be using the central limit theorem in order to use the normal distribution as an approximation for the real distribution that we have. The data must be normally distributed. There's no way around this. If it's not normally distributed, then a methodology that we're going to use here is not going to be applicable. The reason for this is that the test that we've devised using the chi-square distribution is not robust against a departure from normality. What that means is that our test isn't going to work very well if we don't have normally distributed data. And that's why we're being pretty insistent on having this requirement met. So we have to insist on it pretty strictly in order to actually use the methodology for this particular application. Let's look at an example to illustrate how we're going to apply our methodology. So here we have a table that lists data. The data is for heights in inches for a simple random sample of 10 supermodels. Now, if we consider that the heights of supermodels are believed to have much less variation than the heights of women in the general population, we're asked to use a 1% significance level to test the claim that the heights of supermodels have a standard deviation less than 2.6 inches. Now, we are given data, but we're also given summary statistics. So we don't have to use the actual data if we don't want to, but we can if we do. So we can go either way with this. We can use the summary stats or we can use the actual data. But first we need to check to make sure our requirements are met. So the problem statement says we have a simple random sample. So there's the first requirement. And then the data must be normally distributed. So we're going to plug the data into our normal quantile plot and see what we get. And looking at this particular data set, we don't see anything that's too far out of the norm. most of the data points rather are adhering closely to that red line, and we don't see any real set pattern that the dots are making with the line. So it's pretty safe to assume that yes, we have normally distributed data. Now let's actually get into the hypothesis test now that our requirements have been met. We can express the claim that the standard deviation is less than 2.6 inches as sigma is less than 2.6 inches. This is the symbolic representation of our claim. So now we get to write our hypotheses. So the null hypothesis is going to be a statement of equality, just as it's always been. And then, because there's no equality expressed in our claim, we're just going to take the claim and express that as our alternative hypothesis. So now we have our null and alternative hypothesis written. We have a significance level alpha of 1% that comes from the problem statement. And so now we're looking for sample standard deviation because we're making a claim about population standard deviation. Keep in mind that the methodology we're going to use, however, is going to go through the variance because, as we learned earlier, the standard deviation is a biased estimator, but variance, which is the square of standard deviation, is an unbiased estimator. Let's calculate our test statistic. So using the formula that we just looked at a little while ago, we plug in what we know. So we have 10 data points in our sample. So degrees of freedom will be 10 minus 1. We have a sample standard deviation, and we're going to assume that our null hypothesis is true. That means we have a value for population standard deviation, which is the claimed value, 2.6. We plug all these numbers in, punch it out on our calculator, and out comes 0.852. Now we're ready to decide our test results. So we can do this in one of two ways, just as we've done before. If we use the p-value and compare that to our significance level alpha, we find the p-value is going to be the area under the curve to the left of the test statistic. So we calculate our test statistic on the previous slide, 0.852. We plug that into our chi-square calculator in StatCrunch, and out comes our p-value of 0.0003. Now, because this p-value is less than our alpha value of 1%, we're inside the rejection region, and therefore we're going to reject H0. Alternatively, we can compare the test statistic with the critical value. So the critical value is going to come by putting our alpha level into our chi-square calculator, and the horizontal axis value that corresponds with that area is the critical value, 2.09, or 2.088 if you go to 3 decimal places. Now, our test statistic is less than our actual critical value. So that means we're inside the rejection region, and therefore we reject H0. So either way you do this, you're going to come up with the same conclusion. So we rejected the null hypothesis, and we did so on a one-tail test. That means we conclude there is sufficient evidence to support the claim that the standard deviation of the heights of supermodels is less than 2.6 inches. Let's take a look at some of the things that we need to be aware of when we're actually performing hypothesis testing on standard deviations in StatCrunch. For most of the problems that you're going to be assigned, there's really a single option in StatCrunch that will get you most of what you need. So go to Stat, Variance, One Sample with Summary. Of course, if you get a problem that has a data set that you can download into StatCrunch, then you're going to select with data instead of with summary. But for the most part, you're just going to be given a sample standard deviation and asked to do a hypothesis testing on the population standard deviation. So, once you go into your options window, remember that what we're doing in StatCrunch is we're getting to the standard deviation through the variance. So the numbers that you put in for sample variance can't be the standard deviation. You have to square the standard deviation in order to get variance. You also have to square the claimed value when you're putting that into your hypothesis. So don't forget that you gotta make some adjustment in order to use this out in StatCrunch. So if, for example, we have a sample standard deviation of 3.8, then the number we're going to put in for sample variance is 14.44. We have to square the 3.8 in order to get the right number to put into StatCrunch. Likewise, if we have a claimed value for our null hypothesis of 4.4721, then we're going to have to square that to get the right claimed value number to put in to the hypothesis test in StatCrunch. Once you get your results window out after pressing compute, you don't need to take the square root of anything. Back when we were doing confidence intervals, you needed to take the square root of your upper and lower limits to get the right answer out. Here, we're looking for a test statistic and a p-value. And as long as you put the right numbers in, those values are going to be the same. So you don't need to take the square root of anything in your results window. Just take the test statistic and the p-value straight off the results window. As always, the test statistic is the second to last value in the results window, and the p-value is the last number in the results window. Let's take a look at calculating critical values in StatCrunch, because sometimes you're going to be asked to find a critical value, but they don't give you all the information you need to use the hypothesis testing menu options in StatCrunch. In that case, you're going to have to use the distribution calculator, which for standard deviation will be chi-square. So once you pull up your chi-square calculator, make sure you put in the appropriate numbers of degrees of freedom up at the top, and you're going to put the significance level alpha. Since this is an area underneath the curve, you're going to put the significance level alpha to the right of the equal sign in your probability calculation. You also want to make sure that your inequality drop-down in the probability calculation matches the inequality from your alternative hypothesis. Once you have everything set there, then you press compute, and the critical value is read straight off the calculator. Remember, your critical value is the boundary for that area under the curve that is the critical region. And the area of that critical region is alpha. If we have a two-tailed test in StatCrunch, we're going to make a slight adjustment, but we'll still continue to use the chi-squared calculator. When we do, we're going to select the between option up at the top of the calculator. Now remember, when you select that between option in a StatCrunch distribution calculator, you're looking at the area in between the tails. Select your degrees of freedom. You'll put that up at the top as you always have. And then you're going to have to make some adjustment with the area that you're looking for. So if your alpha level is 5%, because the calculator is calculating the area in between the tails, you want the complement of alpha, which in this case would be 95%. So put that area into the right side of your probability calculation, press compute, and out comes your critical values. And again, you just take those right off the calculator. No further adjustment needed. Let's look at an example problem to illustrate what we've learned about hypothesis testing on the population standard deviation. Discarded plastic for 1 week from 62 randomly selected households were weighed and we have a mean weight of 1.911 pounds and a sample standard deviation of 1.065 pounds. This is a similar problem to what we looked at in the last lecture. In fact, it's the same problem, except that now we're asked to find answer the same questions with respect to the claim that the weight of discarded plastic has a standard deviation greater than 1.5 pounds. Again, let's look at each of these questions individually. So the first question we're asked is, what are our hypotheses? Well, first we want to think about the claim being made. So we have the standard deviation greater than 1.50 pounds, so sigma greater than 1.5. This is the symbolic representation for our claim. The null hypothesis will always be a statement of equality. So we take the population standard deviation sigma and set that equal to 1.5. The alternative hypothesis typically reflects the claim. In this case, we can actually reflect the claim in the alternative hypothesis because there is no semblance of equality in the symbolic representation of our claim. So therefore, we're just going to adopt that as our alternative hypothesis. Note that we have the match between our claim and our alternative hypothesis. And using the greater than inequality sign tells us we have a right-tailed hypothesis test. Now let's tackle the next question. What is the test statistic? So in StatCrunch, we're going to go to Stat, Variant Stats, One Sample, with Summary. We enter our information into the options window and press Compute. Now, keep in mind, the sample standard deviation is 1.065, but the option for the StatCrunch calculation is asking for variance. So we have to square 1.065 and put that number, 1.134225, into the appropriate field in StatCrunch. Likewise, we need to square the claimed value for our hypotheses. So we don't put 1.5 in for our null hypothesis claimed value. We're going to put in 1.5 squared, which is 2.25. Make sure you square these numbers when you put them in. Sample size is sample size. You don't need to square that number. But the other two numbers, yes, square them before you put them into StatCrunch. And then as always, make sure the drop down on your inequality with the alternative hypothesis is matching. Once you have this information in, you can press Compute, and you read the test statistic right off the results window. So there's no need to take the square root of anything. So our test statistic will be the second to last number in our results window. And so we have a test statistic value of 30.7501. If we want to know what the p-value is, which is the next question we were asked, we're going to take the last value in our test results window. It will be 0.9996. Now, the next question we're asked is to decide whether to reject the null hypothesis. So again, if we're inside the rejection region, we're going to reject H0, but if we're outside the rejection region, we fail to reject H0. So here we have our critical region of 5%, which is our alpha level. That gives us a critical value of 35.17. So now we're going to compare our area of our p-value with alpha. Go back to our results window. The p-value is the last number listed in the results window, which is 0.9996. This is greater than 0.05. Therefore, we are outside the rejection region, and we fail to reject H0. Alternatively, we can use the test statistic and compare it with our critical value. So here, as you can see on the calculator, our critical value is 35.17. But our test statistic, 30.75. So 30.75 is going to be right about here, which you can see is outside the rejection region, and therefore we reach the same conclusion. We fail to reject H0. What do you conclude from the hypothesis test? So here again we have the 4 standard options that were given for writing our conclusion. The first thing we want to ask ourselves is, did we reject H0 or did we fail to reject H0? In this example, we failed to reject H0. Therefore, we have insufficient evidence. So we want the answer options that say there is not sufficient evidence. That's answer options A and B. So right there off the bat, we've eliminated C and D. Now, the difference between A and B is that A says that there is not sufficient evidence to warrant rejection of the claim, and answer option B says there is not sufficient evidence to support the claim. At this point, we ask ourselves, do we have a one-tail test or a two-tail test? Well, remember back when we were forming our alternative hypothesis, we noted that we have a one-tail test. Therefore, we want to have the wording read support the claim, and that's going to lead us to select answer option B. There's not sufficient evidence to support the claim that the weight of weakly discarded plastic has a standard deviation greater than 1.5 pounds. So keep in mind that because we have that direct reflection of the claim as the alternative hypothesis, we're looking about evidence to support the claim. If we have the sufficient evidence to support the claim, that will come from rejecting the null hypothesis. If we don't have sufficient evidence to support the claim, that will come from failing to reject the null hypothesis. Let's look at another example. And yes, this is the same example problem that we saw in the last lecture. The study tracked 20 randomly selected students and found their mean time to graduate from college was 6.5 years with a standard deviation of the sample of 3.506 years. So same questions as before, but now we're asked to answer them with respect to the claim that the standard deviation of the time to graduate is 3 years. Again, let's look at each of these questions one at a time. So the first question, what are our hypotheses? Well, the first thing we want to do is think about the claim that's being made, which is that the standard deviation is exactly 3 years. That's the claim. The standard deviation is 3 years, so sigma will equal 3. That's a symbolic representation of our claim. Remember that the null hypothesis is by definition a statement of equality. So we're going to select sigma equals 3 as our null hypothesis. Typically, we reflect the claim in the alternative hypothesis. However, in this case, we can't do that because equality, by definition, goes with the null hypothesis. So we have to take the complement of our claim, which is that sigma is not equal to 3. We cannot directly reflect the claim in an alternative hypothesis because equality, by definition, belongs to the null hypothesis. So we have to write what would be the opposite or the complement of our claim. Notice that we now do not have a match between our claim and our alternative hypothesis. Using that not equal to sign in our alternative hypothesis tells us we now have a two-tailed test. Next question we were asked is, what is the test statistic? Again, we're going to go into StatCrunch and look at stat, variant stats, one sample with summary. When we get to our options window, we're going to put our values in. Remember that you have to take the square of the standard deviation in order to get the variance. So don't put 3.506 into that first field. You want to square that number, get 12.29203, and that's the number you put in for the sample variance. Likewise, for our claimed value in our null hypothesis, don't put 3 in. You want to put 9 because 9 is 3 squared. You have to square the numbers to put them in to the fields here in StatCrunch. Sample size is 20. That's going to stay 20. So don't be putting 400 in. You want to put 20 in. Sample size is sample size. When you press compute, you get this lovely little results window come out, And you don't have to take the square root of anything. Just read the number straight off the window. So our test statistic is the next to last number there in the results window. In this case, 25.95. The next question asks us about the p-value, and that's also in the results window. It's always the last value listed there in the results window. In this case, 0.8684. Now we can decide whether to reject the null hypothesis. So, looking first at p-value, if we're outside the critical region, we fail to reject H0. But if we're inside the critical region, we're going to reject H0. So, comparing our p-value with our alpha level, the p-value is going to come from our results window. It's the last number listed there in the results window. When we compare 0.8684 to 0.05, we find that our p-value is greater than our alpha. Therefore, the area for our p-value cannot fit within our critical area, which is our rejection region. Therefore, we fail to reject H0. Similarly, if we were to use the test statistic and compare it with our critical values, notice our critical values are here. They are the boundaries for our rejection region. 25.9 is going to lead us somewhere here, right here in the middle. So we're outside the rejection region, and therefore we reach the same conclusion. We fail to reject H0. What then do we conclude from the hypothesis test? So here we have the same 4 standard options that were given previously. The first question we ask is, did we fail to reject H0 or did we reject H0? Here in this example, we failed to reject H0. Therefore, there is not sufficient evidence. So we're looking at answer options A and B. Because answer options C and D say there is sufficient evidence. And we can't select those because we didn't reject H0. We failed to reject H0. So the difference between A and B is that A says evidence to warrant rejection, whereas B says evidence to support the claim. Did we have a one-tailed or a two-tailed test? Well, think back when we were looking at the alternative hypothesis, we noted that we had a two-tailed test. Therefore, we want the wording to say evidence to warrant rejection of the claim. So the answer option that we're going to select here is answer option A. There is not sufficient evidence to warrant rejection of the claim that the population standard deviation of the time to graduate from college is 3 years. Keep in mind that when you have that two-tailed test, the wording you want to say in your conclusion is warrant rejection of the claim and not support the claim. And then, depending upon whether you reject H0 or fail to reject H0, you're going to say you have sufficient evidence or you do not have sufficient evidence, respectively. Let's talk for a moment about confidence intervals for concluding hypothesis testing on standard deviation. Earlier, when we looked at population hypothesis testing for proportions, we saw that the confidence interval doesn't always produce a reliable conclusion. We then learned that that's not necessarily true with hypothesis testing on the population mean. So we can use a confidence interval on a population mean to decide a hypothesis test. They're just as reliable as the more formal methods of using test statistic or the p-value. This is also true for population standard deviation. So when we make a confidence interval on the population standard deviation, that's going to be just as reliable for concluding our hypothesis test as using a critical value or with a test statistic or p-value with a significance level to conduct a hypothesis test on the population standard deviation. And as always, our confidence level for that confidence interval is going to be the complement of our significance level. So we take 1 minus alpha, and that is the confidence level for our confidence interval. So if our significance level alpha is 5%, we want to construct a confidence interval with the 95% confidence level. That brings us to the end of our lecture. If you have any questions, you know what to do. Otherwise, I will see you in class or the next video. Thanks for watching.